name is Haghighi. I'm a developer advocate at IBM. So basically, I head up developer ecosystems across Europe. But I'm like everyone else, I'm a developer. So basically, sort of my life is all about developers, and we are basically trying to, form a meaningful relationships with developers in different cities and geos, mainly in, tech hubs across Europe. I mean, that's part of my job. So we are in London, Paris, Berlin, Amsterdam, Tel Aviv. And we are going to have new teams in Spain, Italy, and CEE, which is like 27 countries. So we basically run workshops, some meetups, like Tech Talks kind of a style. And it's basically, the way we do that is like, bring your own laptop, and we're going to show you how to create something quite cool from scratch on IBM. But basically, we try to be quite brand agnostic. We say, hey, that's the technology. But it's up to you if you want to use IBM Cloud as your backend, or AWS, Google, or Azure. So we have grown our community dramatically over the past 3 years, because as you know, IBM used to be very much B2B model, but now we have this B2C connection as well. So individual developers in startups, universities, enterprise basically are now using IBM Cloud, using different offerings in IBM Cloud, basically, and which is quite exciting. So that's my current job. But then, if I want to talk to you about my journey in the Java ecosystem, I used to work as an advocate at Sun Microsystems back in 2007. So I was only 21 years old. And I was like so excited because Scott McNeely, the CEO of Sun, came to Imperial College. And he basically sat down with us and told us, hey, we want you to go out there and get developers and students interested in Sun technologies. And I was like, wow, this is amazing. So I used to program in Java, but then I basically got to know a vast ecosystem of Java when I joined Sun. So Netbeans became my de facto IDE for running and writing all my applications. And basically something that happened that got me really excited was like that little box, as you can see here, that is called Sunspot. I'm going to tell you more about this. So that's actually a very small sensor and actuator platform that it no longer exists, but you could basically program it with Java ME, J2ME. That was quite exciting because back then, as an embedded engineer, I had to write every single line of code, like in C for, let's say, microcontrollers and microprocessors, whether it's like TI or, PIC, you name it. But then I basically got something which was amazing. I could just run everything, and then having multiple applications running concurrently, because it basically supports midlets, which was like, having multiple applications running in parallel, like the Nokia phones back then, like those, kind of multiple applications on Nokia. So it was fantastic for me because it kind of, got me into a massive area of wireless sensors, and I could, prototype things rapidly. I did it after, Sun was acquired by Oracle. I worked a little bit for Oracle, but then I left and joined University of Bristol with the BAE systems and some other governmental organizations. We started doing research into complex systems. And I had to design an operating system from scratch for drones and other things. And I basically did that first in Java. And then I had to basically do it in different programming languages. Later on, I joined Intel as a research scientist and the technical lead. And I worked between Intel and the Intel labs in Portland and Santa Clara, and the universities and the mayor's office in London. And then now I'm at IBM. I'm basically doing the same thing, but in the software and cloud side, because at Intel, I used to convince people to switch from ARM to x86 for IoT. But then in IBM, I'm trying to convince people that IBM is a better platform to create your own solutions. So when I mentioned Sunspot, that's basically the platform. It's just a very small sensor box. with a processor board, battery, and then the sensor board comes on top. And it's quite customizable, so we could easily add and remove sensors and actuators. You've got full access to the GPIOs, and this is 2006-07. Like, imagine, back then, Raspberry Pi didn't even exist, and that's basically based on ARM. And the batteries were good enough, like the platform was good enough to run for days, if not weeks and months, basically. And it basically enabled a lot of researchers across the globe, from Berkeley to Imperial and other places, to experiment with what we call IoT now. Back then, wireless sensor and actuator networks. So, as I said to you, for part of my PhD, I had to design a system. I had to basically make those sensors quite smart. And for that, basically, I combined, two different types of algorithms. One was auction-based algorithms, and the other one was game theory. Auctions are basically for making sensors collaborative and kind of cooperative, so they start talking to each other and start kind of, like eBay. For instance, you're bidding for something, so sensors basically start bidding for a task to execute that based on the resources. But then game theory, on the other hand, is something that you've got to look at how you can maximize your own profit or benefit without considering others' decisions. So I combined those two together, and then I created a middleware which later on turned into an operating system, and it was like 80,000 lines of code in Java. But then I had to actually turn it into system C and C++. So if you're interested in that, you can look me up, just my name on Google Scholar. You can see lots of publications. It basically talks about every single details of those components that came together in Java programming language. But then my current project, which is quite cool, at least that's what I think. So I've got 125 Raspberry Pis. It's a cluster. And some Raspberry Pi Zeros, Raspberry Pi 3, even Raspberry Pi A plus. So I basically combined them all together to create this kind of platform, or kind of, to basically showcase the power of Java and also parallel processing for resource constraints devices like Raspberry Pis. But obviously, all these devices are mains powered, but then there are possibilities that you can make those devices battery powered, and there are already lots of applications out there. If you wonder how those, I basically had a few nodes, and you're like, that's not 125 Raspberry Pis. Basically, they're like 4 Raspberry Pi Zeros on top of a Raspberry Pi 3. And that's basically like, each one of those is like 5 Raspberry Pis altogether. And the system, and basically I've got like a ledger in a Raspberry Pi A+. So whatever happens here, because I've got an array of LEDs, 8 LEDs on top of each Raspberry Pi Zero. So whatever happens in there, you can actually see the processing with the color of LEDs changing. And at the same time, you can see the ledger on each side. If that's basically the current operation or previous operation and how much you've actually progressed. So I use this platform for blockchain. I've used it for a Spark. But I'm basically, at the moment, I'm trying to... sorry. Even when you put it on the sleep mode, it still comes up. I called my boss once when I was talking about her. I'm not joking. So at the moment, I'm trying to just program them and make them to work together in a way that I'm going to explain to you later on. I'm setting up a web page for this because it's part of the book I've been writing, and I'm basically going to make all the information about this platform public and open source. So everything's going to be open source. Anyway, so when we talk about artificial intelligence, it's a very broad category, and people use those terms kind of in a way that is not very well defined. So if you want to talk about machine learning, deep learning, and artificial intelligence, you've got to look at it this way. You've got the umbrella for AI that basically talks about kind of mimicking humans' behaviors, but then you've got machine learning that you learn with data sets, but then you've got the deep learning side, which is making the machines powerful enough, by giving them enough data that they basically start writing their own algorithms. And that's how AI is kind of defined in terms of machine learning and deep learning being as a subset of AI. But then, there are different definitions for that. For instance, John McCarthy basically says the science and engineering of making intelligent machines. That's a very broad and generic term. But then, Tom Mitchell basically says, from the logic perspective, experiment E with respect to some class of task T, and that's basically the result. Obviously, there are various definitions for machine learning, deep learning, and AI. But then, I think this is actually quite nice because you're saying that we give computers the ability to learn without being explicitly programmed or supervised. That's actually quite interesting. But the most important part is about putting data into the system, feeding data into the system, letting the system to kind of extract features and then classify and then give you the output. Whereas with deep learning, you've got like a black box in the middle. That's the neural network, ANNs or DNNs basically. And whatever happens in there, you're not fully aware of the system's decisions behind that. And that makes deep learning quite interesting and at the same time not usable or not useful or kind of reliable enough for apply to different fields. But let's say for the machine learning side, I just want to give you the definition before we go deeper into the field. For the machine learning side, let's say that's the way I define it. Let's say you want to build a robot that opens doors. So it's quite simple. You program the robot to walk up to a door and then pull it open. But then the problem is what happens if it basically goes to an automatic door or a door that needs to be pushed. So for that, you need to feed enough data to the machine to learn from like thousands of different doors, like by the pictures, the movies, or whatever, to learn how to push a door open or interact differently. And that's basically less programming on your side because you don't have to program it for various possibilities and letting the machine learn from that data set. And that's basically machine learning. I think that's a kind of a simple definition of machine learning. Like, for instance, if I ask you, can you recognize the characters in there, like the numbers? Obviously you can, because it's just a grayscale image in a one-dimensional array that kind of gets translated. That's just a softmax or regression, basically, logistic regression. So making that, embedding that into a machine, that makes it possible for us to have machine learning in IoT nodes. And it's quite simple. It's not difficult at all. Like the one that I mentioned earlier about combining auction-based algorithms and game theory, that is a very simple operation for basically combining two different algorithms and letting the machine learn from that. But the interesting part is here. So back at Intel, we had this amazing project involving University College London, Imperial College, the Mayor of London's office, Queen Elizabeth Olympic Park. That's the Olympic Park that was used back in 2012 Olympics. And we wanted to basically use a kind of an environment to experiment with different aspects of IoT. And billion device challenge is one of those important aspects of IoT. And in that, basically, you've got communications, you've got power saving, you've got node management in IoT. And basically what we did, we were given the Olympic Park in London. Has anyone been to the Olympic Park? Yay, John. Oh, cool. Oh, we got people. Oh, great. So this is a very nice park, first of all, but it's just the problem was that like back in 2012, after the Olympics, people actually didn't like going back there because there was nothing going on. And the mayor's office, they've decided to actually bring some interesting projects to the park and use it as a kind of a test bed and attract people to come to the park again. And also open up new university campuses, lots of activities. But for us it was quite interesting because we could, by putting all those sensors and technologies in the park, we were just it was like for us kind of experimenting with a mini city, because you've got all aspects of a city inside this park. You've got roads, you've got rivers, you've got rail lines, lots of things. Sport venues and residential areas. So it's like you've got a mini city within London. So it was quite a good opportunity for us to have this park for a couple of years to experiment with. So the first point for us was the managing the communication side of IoT. And when we talk about communication, IoT devices, they have different communication capabilities, like different transceivers, radios, like cellulars, like Bluetooth, Wi-Fi, you name it. So we wanted to know what it's like to have multiple communication transceivers in a node, and how the node can actually decide how to switch between different transmission kind of means based on certain values or certain parameters and dynamics. So we thought, let's use the most energy efficient kind of radio communication protocol, which is, there are multiple ones, but like LoRa is one of those really good ones because the energy consumption is quite low, but at the same time, you can get up to 20 kilometers of communication using a single device. I mean, the definition of LoRa is there, but like it's one of those technologies that you can actually create it, like build a network right at home. I mean, you don't even need to get any sort of permission. And it allows for thousands of devices to communicate with a single base station. So I basically went on top of that beautiful structure. So the Orbit is called in London. I call it the Eiffel Tower of London. So basically, we installed that receiver on top of this beautiful structure, and that's at 114 meter altitude, and it covers 22 kilometers radius. So not only the park, because the park is like 5 kilometers by 6 kilometers probably maximum, but we could cover a large area of London by just having this receiver on top of the Orbit. And then we basically started kind of building devices. So those are the devices to send signals from different parts of the park and see how those signals are being received. And everything in that box basically is programmed with Java. So I've got JVM, and I'm going to get to that. But we thought, okay, let's put more radios into the device. So in addition to LoRa, we put Wi-Fi, BLE, and 802.15.4, which is like Zigbee protocol is based on that. And the device should become smart enough to switch between different radios based on the noise, based on this power, based on the sort of data it wants to transmit. If it's like a massive amount of data, it can just switch to Wi-Fi and send it quickly. If it's just like a small kind of metadata, we can just use LoRa or BLE. And the BLE side is actually quite interesting because the park owners, they've started putting this app, kind of making it available for public to put it on their phones. So when they walk around the park, the app capture that data and send it to the servers. So the nodes were sending data through people. So people were basically data collectors or relays. And that's basically, if you go to London, to the Olympic Park, you can see these beautiful, I call them beautiful, they're beautiful, but like those yellow boxes on top of some of the lampposts. And we thought, okay, that's fantastic, but then what's the use of that? Let's do something with it. So that was the next phase. The next phase was adding some sensors. And we had meetings with the ecologists in the park, and they were interested to get microclimate data, water quality, and bat data. He was like, that was the most mind-boggling, like, when they said, you're interested in bats, and I was like, bats? And they said, yes, because bats are actually very good indicators of biodiversity of an environment. So they are like humans. They have social calls, stress calls. Obviously, we don't hear that, but they've got that. So that's like using some sonar sensors, you can easily capture that and match it to a set of, a data set of different bat calls and species, and find out whether the bats are happy or unhappy, and how many of them are actually in the park, and how often are they, communicating, interacting, etc. So they said, okay, fantastic, why not? So we installed an acoustic sensor in the boxes as well. So we had microclimate, which was like, different kind of temperature, humidity, And then water quality was like on the river side. We had like pH and oxygen level and etc. So what we did, we put a gateway. The gateway was the LoRa receiver that I told you on top of the orbit. And all these sensors from around the park, they were like sending data to the LoRa receiver. And then we made that data available to public so they could easily just see what's happening through some REST APIs, everything again done in Java. And the most important aspect of this is like all these nodes were kind of creating a layer to process data collaboratively. And that was something that we didn't even expect we could actually do, but like we ended up making that happen. Not only they were sending that data to the receiver, but also they created a layer to interact and process data in parallel. So to give you an idea of the number of messages we get from the sensors, we basically use Unity to simulate the number of messages coming from different parts of the park. So that's about 6,000 messages per second coming from those boxes. And you can imagine what is it like to have that sort of kind of, intense communication happening, every second, every millisecond sometimes. And not only that, because of the bat species, we had to actually capture the sonar, the acoustic wave of bats calls. And that was like 1 gig of data sometimes. And imagine like sending that data to the base station to aggregate and mine. That was a massive, massive, it was very costly in terms of the power efficiency of the boxes and also the bandwidth. And at the same time, as you can see the heat map, like over Sundays and Saturdays, sometimes over the weekend, we noticed that there was like massive noise coming from the park. And it was just because the West Ham United Stadium is actually inside the park. So people who used to come to watch the match, they used to bring their mobile phones, that's it. And in a single mobile phone, you've got like 2.4 gigahertz like for Wi-Fi, you've got 5 gigahertz nowadays for your, if you've got dual bands. And then you've got your Bluetooth on. So all that noise was basically generated. So the boxes had to be intelligent enough to switch between different radios when the noise ratio was high. So the Wi-Fi wasn't actually good enough for them to communicate their data, so they had to use LoRa. And if they had like people around them, they could actually relay data through Bluetooth. So just to give you an idea, what is that like for ML in IoT? You've got like different algorithmic techniques basically to optimize latency, throughput, like for radio communication. Energy, data rate, signal strength, and packet error rate. Those are like the most typical ones that the IoT devices should use, because we always look at it from the data aspect, not from the optimization of the device itself. But when it comes to edge processing, these are the most common types of edge processing operations basically at the edge. Sorting, aggregation, getting rid of duplicate data points, some analytics, but they must be very, kind of not quite expensive in terms of energy cost and the bandwidth, because otherwise then it becomes quite difficult for you to deploy those nodes and keep them, their, longevity for a long time for those nodes to operate. So this is just one example of what we did. So if you look at, for instance, this side, for 26, 27 to 30, and then 21 to 25, so those are the locations around the park. We had no signal whatsoever, even though we were using LoRa, because they had like massive structures, cement and stuff. It was like kind of blocking the signal completely. So we had to do something to get that data through. So by using machine learning, and it was just a very simple operation, we managed to get some of those data in by changing some of the specifications of the LoRa communication. So for instance, by changing the SF, which is a spreading factor, from 7 to 12, but then that obviously comes with energy cost. Very quickly, we could actually get the data through. And that's basically the sensor looks at the SNR, signal noise ratio, and the RSSI is received signal strength indicator. On the edge processing side, we were looking at the data coming from the sensors. So we call that anomaly detection, for instance, if all the data streams are coming and then suddenly all of them goes down or up or something happens. So we wanted the boxes to be capable of analyzing data and detect those anomalies. And as you can see from those flags down there, those are the ones that the boxes itself, themselves, they were actually able to flag every time we had some anomaly happening in the system. It could be for for multi-streams, as you can see, like it was again flagged. It could be for multiple streams at the same time going down, or kind of going down and back up again, like reversive, we call this recursive. And then some of them basically going up or going down, like different types of operations that happens with signals in IoT networks. But like you can look at this Internet of Things. There's going to be like 50 billion devices. I'm sure now the estimation is way higher than that. But obviously, the operation that I just explained to you, it can happen in three different paradigms. So it's either silo only, or edge only, or edge and cloud. Some people have different categorizations for that. They add like 4 or 5 to combine different ones. But that's how you can actually do it. You either have to do it on the node, or just do it on the gateway, or do it on the gateway and the cloud. Those are the most common types of data processing in IoT networks using edge. Those are like kind of boring definitions from the industrial side, but the most important points here is to, for using edge computing, is to get rid of latency and transfer cost, basically. And latency is, if I capture an image from a camera and I want to send it to cloud and get the results back, that's going to be like a few seconds, let's say, in some cases. So you want to actually get rid of that latency if your operation is critical, like let's say for defense and military applications. If you have a massive amount of data and you're running it on your nodes are running on batteries, then it's going to become quite expensive, because your nodes are going to use a lot of energy to transfer that bit of data. So that's why you need to bring that intelligence to the edge. But how do you do that? So gateways, you can't have a full-blown computer, like fully functional computer in there. So you have to use gateways. And for gateways, that's the part that Java basically kicks in like properly. So far I was just talking about programming the nodes using Java. But then we have something like the OSGI. It's called OSGI. It's been around since 1999. Many people say that it's dead. It's not dead. The org is quite active, and I'm going to get to that. But basically, Cura is a project that is a platform that gives you the sort of software you want to run on your gateways. And it's very capable. It's basically, you can just put it on your gateway, and it takes care of everything for you. As you can see, I've got all the specifications of what it does. The hardware abstraction layer is something that is quite important. It's fully open source. You don't have to pay for it. And obviously, you've got the modularity as well for updating your nodes, for running this type of applications you want on the devices. And that's the architecture of Cura. But in a nutshell, if you want to look at Cura, basically it just provides an OSGI-based container for IoT applications running in service gateways. So you can turn a small device, like a resource-constrained device, in a proper, powerful IoT gateway. And we've done that. I've done that basically using x86 architecture, using ARM architecture. And the APIs are quite powerful, because you can access all your devices, you can manage your devices remotely, and it's quite reliable. And on the OSGI side, OSGI is a Java framework, and it basically talks about two things. One is the bundles, and the other one is service registry. So when you have like a modular component involved, like you can let's say you deploy your application and you want to update it, or you deploy your application and you want to kind of add new services that are available on the node, but you didn't want to do it from the beginning. I'm just giving you a quick example. OSGI enables you to insert new modules into your system, and your system basically can easily kind of get that injected into it and start running with the new modules. And you can even have new libraries if I want to talk about like in a programming terms. And then the service registry basically allows you to look at what's actually happening, how many of those services are being deployed and it's actually running at the moment. And it's been around, as I said to you, it's been around since 1999. There are lots of companies out there that are using Kura as the base of their products. Eurotech is one of them. They're selling their gateways for 1,000 or even more sometimes. And it's just basically just making sure that the security side and the vulnerabilities, everything is actually addressed. But you as a developer, you can easily just get a Raspberry Pi and put Kura on top of Raspberry Pi and have your gateway up and running in your home or wherever you want. And you can actually, the nice thing about Kura is you could have multiple gateways and kind of interconnect them to run multiple applications concurrently and have all those gateways to communicate and collaborate for your network. I've basically highlighted some of those specifications, but obviously MQTT messaging is one of the most common way of, MQTT is actually invented by Andy Stanford Clark. So he's a good friend of mine. He's the CTO of IBM UK. So for instance, MQTT is now the backbone of, I would say 99% of IoT app devices out there. So they've got MQTT running on the, as their underlying kind of communication layer protocol. And it's quite simple. It's a pub/sub. So you subscribe for a topic, and then once that topic is available, it basically goes and retrieves that. Some of the other things like the synchronization, Kura can help you do that. And also like, using serial and USB communication on the bottom, Kura basically makes that available to you. So as I said to you, you've got different routes basically into using Kura. You can go for industrial M2M gateways, or you can just like get a BeagleBone or a Raspberry Pi and put Kura on top of that, and that's it. You've got a IoT gateway. It's very capable. Like, the way I'm telling you, and I'm quite surprised that not many people are using that, because I can see sometimes people are programming the Raspberry Pis to retrieve data and do all these operations. With Kura, you've got everything open source, and it's just modular. You just basically put those modules like libraries, you make that available, and your system is up and running again. You can have your own smart things or Nest, in your own home. If you are a good programmer, which most of you are, you can easily make that happen. And if you look at it from the commercial perspective, obviously the Oracle version is the commercial stack, is based on Oracle JVM. But if you want like the OpenJDK version is also available. So you can get two flavors, the open source one and the commercial one. But as like you can get access to both of them and you can give it a try and see what it's like. But obviously the one on the right side is mostly about the security patches and making sure that you get enough support in terms of maintenance. Yocto is another important aspect of that, because Yocto is available for Raspberry Pi, for x86 and ARM, so you can actually put it on, I would say 99.99% of all the devices out there, they're based on, you can actually run Yocto on top of that, and it's a very small footprint Linux. But then when it comes to visual recognition, obviously what I said just now is not good enough for you to run visual recognition application on top of your nodes. What can you do about that? Because Kura is only good for running small Java applications, and data mining and all those sort of things are impossible to do. What you can do for that is, for these sort of applications, this is like a simple joke, but like, what if you want to have your system to be capable of detecting some sort of anomalies, as we call it here, like, thieves kind of coming to a bank or something like that, instead of like, as you see in movies, like a heroic kind of employee kind of jumping to press the button. What if your system becomes, intelligent enough to do that? So I'm going to show you a demo of basically the same thing happening, which is done by IBM on IBM Cloud using Power AI. So you see, a person comes in, and as soon as the gun is basically drawn by the security, the system triggers the alarm. So nobody needs to press the alarm. The system is intelligent enough to realize that there are two persons, one of them fallen down. So this is all happening in the cloud, and your IoT device can just stream that video up to the cloud. You don't need to run it on the device. But if you want to run that sort of kind of data processing on your device, there is a way for that. And there are other applications for it. Let me show you this. So this is for like reducing thefts in supermarkets. So if he tries to kind of avoid scanning an item, you see like basically put it like under the. See, it's detected. So you just pass it underneath. This is quite common actually in supermarkets nowadays for self-checkouts, or like for surveillance. Drones being able to do that sort of processing to realize what's going on, like a person walking around the parking lot, things like that. Or like for this one, somebody crossing the road and is very close, kind of that was a very near miss basically. See like a bus kind of going around, or a number of kind of let me see. The number of vehicles entering an area to kind of estimate the traffic, or sending some sort of text messages and alerts. Those systems are also available out there. So you can use a cloud backend to analyze data, but then your devices could connect to them. How that's going to happen? So I'm going to tell you now. So it's not complex. So you could have all these sort of kind of operations, CNN being the most important one, happening, on your devices. So you could basically enable your devices to recognize images and basically flag or kind of look for interesting activities in footage. And for that, obviously, you need to have some sort of kind of TensorFlow running on your devices. Obviously, you can't have the full version of TensorFlow running on your Raspberry Pi, but there's this thing called TensorFlow Lite, which is available even for Android, for BeagleBones, even for Raspberry Pi Zero. And that's just a runtime that basically allows you to run your build model on top of a device. So you can build your model and then run it on top of your device. So, and I'm going to show you in a demo how you can do that. So, and the reason for that is why you can't actually do that is because you've got CPUs, not GPUs. In a GPU, you've got thousands of cores, that allows you to do a proper data mining. Whereas on a CPU, you only have like a couple of cores, and that's used for the execution of your code rather than kind of mining and analyzing data. So if you want to have that sort of device with a GPU embedded in your IoT device, Jetson TX from Nvidia is very capable. The new version of Jetson TX2 actually has 512 cores. So you can actually use those CUDA cores to build your model to for inference, and then it basically got a good CPU as well on board, so you can do your operations running Java, anything else basically on top of that. And in terms of memory, it's also very good. You've got 8 gigs, 16 gig, and the size of that device is just this small. It's like a credit card size. So you can add it on top of your Raspberry Pi or next to your Raspberry Pi and have a device that capable out there. And this is something that not many people are quite aware of, and it's available. Like you can buy it now, and it's not that expensive. If you want something like beefy, like something for your gateway, Jetson Xavier is actually is a powerhouse. It's used for robotic application, but the size is this small. You can easily put it in your edge, for instance, for industrial applications, you could have thousands of devices sending data to Jetson Xavier, and then you can run all those very heavy mining operations on top of this device without connecting it to the cloud or anywhere else. So that's basically a full-blown computer with GPU and multiple CPUs. You've got 4 CPUs here and a proper kind of accelerator engine on top of this device. So you could have this as your gateway. And once you have those devices, you've got Keras, you've got TensorFlow, OpenCV, like you name it. You've got everything. So your IoT device can become very capable and powerful by just putting these platforms and frameworks on top of your IoT device. But then when I mentioned about the cloud side, how you can actually feed your data to a cloud provider and then get the data back very quickly if you want. So that could be your edge processing using those devices that I've just mentioned, but at the same time, you could have your cloud as a backend, just in case if you want to send the data back to the cloud. And the way it happens is you've got this unstructured and structured, and then you've got the inside. And we use basically for that, we use APIs. And the APIs, you can get it from Google, you can get it from Microsoft, but since I'm from IBM, I'm going to tell you about the IBM side. And it's quite simple. It's just a matter of, obviously most of you know what APIs are, but like it's just a simple URL. You put your data in there, you submit it, and you get the results back. But what happens on the cloud side is not that complex. I'm going to show you how you can actually capture images from, let's say, build a model, and then just send the data back to the cloud and get the results back, whether that matches that model or not, the sort of data you're sending. Some of the APIs, I mean, it doesn't need to be specifically about visual recognition. It could be like something like tone analyzer. You can send an audio clip and see like if somebody's kind of angry or somebody's kind of, not speaking in their native language or something like that. We've got so many things that you can use IBM Cloud for it. And those are like the APIs available. And again, it's not just IBM. All the other vendors have this, but like those are the ones that I can easily tell you how to build. As an example, like you've got, conversation services, natural language, you've got kind of, weather forecasting. All those APIs, you can easily connect them to your Raspberry Pis or IoT devices.
APIs for classification or model creation?
Which one, sorry?
All these APIs, they are actually for creation of the model, or they are for classification of data?
No, it's basically for creation of the model, but it depends. You can actually have both of them. If you want to send your data back to the cloud and wait for that model to be created, obviously you can do that, but it's going to take a long time. But usually it's best to create your model first and then use the APIs to send your data and match it and get the results back. Model already exists. And also you can sometimes get the models available. We have something called Model Asset Exchange, MAX. So those models are available. For instance, if you want to send a photo of a cat and kind of find out what sort of a species this cat come from, is that a Persian cat or something else, you can easily get that MAX model from IBM and run it in your own platform, and it's for free, by the way, it's open source. So you don't even need to capture like 1,000 images of a cat and then cats and basically build your model. Those models are already available, so pre-made basically. And then the other part, before I get to the demo part, before that, I would like to mention that using Netbeans, that is now part of Apache, using Netbeans, you can program Raspberry Pis very easily. So I found this link. I had a video on YouTube. I couldn't find it, but I found it on Instructables, basically, that somebody is going to show you exactly how you can use Netbeans. And it's super simple. One of the things about Netbeans is it allows you to connect to your Raspberry, basically to program, compile and run your program using a portable or let's say remote platform. So instead of running on your own JDK on your machine, you can basically tell your IDE to build a model based on the JDK on your Raspberry Pi by giving the address of the JDK on your Raspberry Pi, which is remote JVM, and then build that model and then run it on top of Raspberry Pi. And that basically takes like 2 seconds, 3 seconds, instead of kind of write your Java code, put it on your Raspberry Pi, for instance, and then Java, doing all the compilation and that. You can actually do it on Netbeans. And the way it happens is you basically need to choose your runtime platform. Instead of your native, you're on your machine, you can choose Raspberry Pi, and this makes it quite quick. I basically use Intel Edison with this. Lots of other things, lots of other platforms. You can easily just program it, and you can have multiple platforms connected, so you can just compile your code and run it on 100 Raspberry Pi at the same time. So you don't need to connect them one by one. So remember that one. This is actually quite useful. So let's get to the specifically about the question you had. So this is the Power AI. IBM Power AI. So here we are going to build a model by just, it's an object detection model. So by, feeding some data to the system and letting the system to build that model. And it all happens on the cloud. So if you don't have enough power on your computer, because on your computer, if you want to run TensorFlow, that's going to take a few hours easily. But and here we're just basically going to, feed the images of Coca-Cola, which is quite in line with Atlanta. You've got Sprite, you've got Canada, like different kind of brands. So you basically feed that in. You have to label it. So you're basically telling the system what sort of image is this one. It's like, for object detection. And it's quick. You see, like, if you've got like, let's say, even 10 images of something, you can easily just put it through. So you've built a model. And also, annotating, labeling these. So yeah, you can even decide, how your system should treat them. Like, if it's like, you give them like, upside down, or back to front. You can easily tell the system to, take into account multiple possibilities of how this image is going to come for pattern matching. You see, the system is now looking at these images from different angles. I decided to have the video instead of running it, live, because I was sure it's going to fail. So now the training of data starts. Look, it's only been like 2 minutes now, 2.5 minutes. So your data is now trained, and now you can actually deploy that. So that model is ready to be deployed. And by deploying that model, I mean, you create an API and then include that API into a Raspberry Pi or whatever machines you have. And there's a test page that basically you can include that API and feed your images and see what it's like. See, now we are basically going to send an image, and the system basically gives you even the threshold, the confidence value for each one of them, saying like, what is it? Like, this is a Diet Coke, not, 99%. The other one is like a Coke Zero, and as simple as that. So you built your, and I can give you one example. So let's say you install a camera on your front door. You basically give all the pictures of your household to the system. You build a model of everyone who is going to be there. And then the system is automatically, and then you build a model with different names saying like, Sally, Sarah coming like home at what time. And you can actually get those kind of messages sent to your Twitter feed or to your email. If someone else comes in, because the system can't actually recognize that, but just sending a simple message up to the cloud and getting the results back, the system can detect whether there's an intrusion, there's someone there who shouldn't be there. Like, that's exactly the sort of technology behind all these small and kind of cheap cameras that you get nowadays. That they've got this object detection or person detection or face detection, basically. So it was that simple. In less than 5 minutes, you can create your model by just selecting the images you want and including that API into a Raspberry Pi or resource-constrained devices. So next, what's on IET Platform? So we've got an expert here, John Walicki at the back. So he can tell you much more better about the what's on IoT Platform. But for most of the operations that I explained to you and all those activities and experiments that I told you about the Olympic Park in London, you can easily you can create your own device and your own platform or your own management layer. But at the same time, you can come to one of the IoT platform providers like IBM and get that all kind of managed and started on a cloud backend like IBM. And it basically takes care of everything in terms of the security side, in terms of the AI-powered portfolio. Even if you are talking about kind of connecting that to your industrial applications, it can take care of everything. And it's quite simple. You just basically get your devices connected to the cloud with an agent that communicates back and forth with your cloud, and you can even have it on your edge devices. So it's quite simple. It's quite cheap, I would say. Like, for a limited number of devices, you don't even have to pay. You can just get the system up and running very quickly. It's one of our top workshops. One of our top workshops is about IET in IBM, because we are quite good with IET, with Node-RED, and I don't know if you've come across those platforms, Node-RED and MQTT, and kind of the technologies that IBM has invented. And in terms of like, the platform, I think this one is a little bit dated, this diagram, but you get everything. If you're in industry or you're looking to kind of, build it for engineering solutions. Analytics is the most important aspect. So once you have all your devices connected and hooked up to the cloud, you can actually create a model in the middle to make those decisions for you, looking for anomalies, looking for interesting data, giving you charts, historical charts, and kind of insights about your platform, your data, and how often they go out of service, or what's actually going to happen if one of your nodes fails. You can basically make all those decisions. You can let the system make all those decisions on your behalf automatically. And then the most important, again, from my perspective, is blockchain service. Blockchain service is also part of the IoT platform. You can include that. So your nodes, if let's say there's an intrusion, somebody's trying to use your nodes to send, fault data or false data, what happens is the service can easily detect that by connecting to IBM blockchain platform. So that's again one of the features of Watson, being quite intelligent, but at the same time having that blockchain services included, embedded into your solution is quite important. Not many vendors can actually do that. I would say IBM is the only one at the moment that can combine that together in one solution. And as I said to you, based on the demo I showed you, you could have visual integration and simulation and extensive number of APIs included in your platform. I've tried that with 50 Raspberry Pis connected to the cloud. It works really nicely, like smoothly without any hassle. Sometimes, obviously, you need to make some customizations if you have a very special application or you have something very specific in mind. But for most of the applications out there, like the common and popular ones, we have some recipes that you can use. We call them code patterns. You can even use the tutorials to learn that. The most important, in terms of manufacturing, transportation, and utilities are the ones that we are focused on at IBM for IoT. Some of the use cases, L'Oreal is actually one of the big companies that is using our IoT service. The other one is a port in Rotterdam that they're basically using IoT services to track shipments and containers, and they're also using the blockchain service in the back end. Sandvik, for mining applications, they're using Watson IoT services, and those are just like a few use cases I'm mentioning. We have hundreds of vendors out there using IoT platform, Watson IoT platform in their backend. Don't want to bore you anymore, but like on the security side, it's actually quite important to look at all those nodes you have out there, because if people can get to those nodes, they can get to your network, they can get to your data. We take care of everything, kind of end to end. We create a kind of a shell, around your IoT devices and your gateways. Again, if you want to have a limited number of nodes, you can get it for free. You don't need to do that. I'm basically writing some tutorials and recording some videos showing people how they can do that with my Raspberry Pi cluster that I showed you in the beginning. So it's all included. But again, I don't want to pitch IBM too much because I know developers, they don't like to be told what to use. So I want you to actually try it yourself, and you trust the system based on your own experiment. And Watson IoT is basically part of this massive portfolio of different companies and organizations involved in this, including the LoRa Alliance that I mentioned to you that we used in the Olympic Park in London, and also like OpenStack, Node.js, Linux Foundation. All of them are already included in the portfolio. And you've got Node-RED, which is quite simple, GUI-based application that you can build your application very quickly. Last but not least, you could have your service running on public cloud, private cloud, or hybrid. And this is quite important for IBM these days because of Red Hat coming into IBM. By having OpenShift and Kubernetes services, you could have all these services running on top of OpenShift and Kubernetes, and kind of move your application, migrate your application with zero customization. So whether you run it on your own servers in your own company, or you want to put it on AWS or come back to IBM, you can easily do that without any zero configuration. Like in less than an hour, you can easily manage your application, manage your entire solution, and move it around. And the hybrid approach is something that goes between the two. Am I over time? Yeah. Oh, gosh. Thank you very much. I'm not going to go through these. These are like all the tutorials. But if you need more information or need additional details about my projects, I didn't talk about a lot of those, actually. I had to make it very quick. But that's my email address, and that's my Twitter hashtag handle. So feel free to contact me. Thank you very much.